Okay, so you guys have seen this plot or something like this at least twice, maybe 3 times over the course of the past couple weeks. And the goal of this tutorial is for you to understand why these data points, which represent measurements of strontium and neodymium isotopes on mid-ocean ridge basalt, MORB, and ocean island basalt, OIB, why they form a negatively sloping array. And this is from Al Hoffman's famous 1997 Nature paper, which I hope you've all read, and if you haven't, you should. If for no other reason than to help you go to sleep at night. You'll fall asleep right away. Oh, no, I never said that. It's a good paper. The isotopic data set hasn't changed considerably. It's still basically the same negative trend, and we want to understand why this trend exists. So what we're going to do is we're going to model the strontium and neodymium isotope evolution of the mantle to try to generate an array that matches this array. And there are 2 things that are going to go on. First, you're going to melt the mantle, and you're going to fractionate parent-daughter elements. So the radioactive parent, for example, Vanna Bill.
You're going to tell them? You're not going to ask them?
The radioactive parent to strontium-87 is what? Yeah. All right, come on. Somebody knows this. A geophysicist has to answer the question.
What's the question?
What's the radioactive parent to strontium-87?
Rubidium.
Rubidium what?
87.
That's right.
Now, how does it decay?
Oh.
With neutrinos. Just don't leave that out.
What's the radioactive parent to 143 neodymium? Samarium what? 147. It's alpha decay. It's actually generating helium-4 nuclei during this decay process. Half-life here, order of 50 billion. Half-life here, order 100 billion years. So the goal here is to fractionate the parent from the daughter and then give it time for decay to set up. And here fractionate parent from daughter, and then you give time to let the parent decay to daughter to generate isotope differences. So you have to, what we're going to do today is we're going to melt the mantle to fractionate the parent and daughter elements, and then we're going to wait variable amounts of time to generate different isotopic compositions that will hopefully lie along this array. Bill.
So I'm going to ask a question of the audience. Does anybody know the relative half-life of the alpha or beta decay chain? So in that previous one, there was alpha decay and a beta decay. So alpha, beta. Anybody know the half-lives?
I said it.
What?
I said it within like 10%.
I know you said it. So it's actually a factor of 2 difference, right? Between the x-axis is half the time that the y-axis takes. Just want to get it into your brain. There's 2 functional forms here. It's the ratio of the parents to the daughter and the half-lives.
Okay, so how do we evolve radiogenic isotopic differences? There are 2 steps. First, you have to fractionate the parent from the daughter. If you don't fractionate parent from daughter, you're not going to generate any differences. So the key is to fractionate parent from daughter, and we do this by melting the mantle. And then you wait. If you fractionate parent and daughter on day 1, you're going to have no isotopic differences.
But isn't fractionation mean an isotopic difference?
No, in this case, you're fractionating 2 elements from each other. You're fractionating their relative abundances from each other. You can have fractionation of isotopes. You can also have fractionation of elements from each other.
There's no significant difference between how 87 strontium and 86 strontium or whatever. They're going the same.
Trying to separate neodymium and strontium, not the isotopes of each from each other.
We're not fractionating strontium isotopes and neodymium isotopes on day 1 when melting happens. Bill?
Pretty like a zero time like ratio between neodymium and
Yeah, at the instant that melting happens, rubidium and strontium is different between the melt and the mantle residue, but isotopically, the melt and the residue are exactly the same on day one.
Yeah, no, exactly. And then you start.
And then you wait.
Yeah.
That's right. So you have to do this, and then you have to wait.
So, Josh had raised an interesting point, and I want to explore it further.
Uh-oh.
Sorry. No.
I'm going to just sit down and we'll let the tutorial. No.
So, Josh was remembering a Knox lecture. And if you remember a Knox lecture, does anybody here remember the heaviest element that was investigated and also shown on a Knox periodic table in which isotope fractionation occurred?
Iron? It went higher than iron. I think
There's a blue one. Blue square.
it was definitely a blue square, yes.
So it's in her diagram, it was thallium.
My next guess.
Does you know which element? All right, here's the tricky one. Who could I ask for this one? What element is to the right of thallium? Sana? All right, if you don't know that, just tell me the isotopes of thallium. There's actually an element that does fractionate that people have looked at by mass fractionation during, say, melting, but really it's during weathering. Heavier than thallium, and that's uranium. But thallium is mass 203 and mass 205. So back to Josh's question. Are we looking at the fractionation due to the isotopes during melting? The answer is no. We know it occurs. We now have mass spectrometers that can look at it. But let me make one thing explicit. The mass spectrometer also fractionates it. And when we're doing these kinds of applications, we remove that fractionation. So even if it's occurring in nature and occurring in the laboratory, we normalize it out during our measurements of it. So it does occur. And in fact, I have seen a paper by Wes Hildreth, forgive me, Wes, in which he suggested that some of the 87-86 variation in the Bishop Tuck might have been due to mass fractionation. And this was a long time ago. And the first response an isotope geochemist has, no, we correct for that in mass spectrometer. So if it happened, we weren't even seeing it.
All right, Bill, thanks. That's a good point. So, two-step process. First, step one, we're going to fractionate the parent and the daughter element, rubidium and strontium, and then samarium and neodymium. We do this by melting the mantle and extracting the melt. Okay, so we're going to use the absolute simplest melt model. It's just batch melting. So let me describe each of these variables really quickly. Here is the concentration in the liquid, the melt, of a particular trace element. Let's say strontium. And this is the concentration of strontium in the original unmelted solid. So this doesn't change. This number goes up and down depending on how you vary F and D. F. What's F? F is the amount of melting. It's the fraction of melting. And the values range from 0, F is 0, no melting occurs, to F is 1, where you have 100% melting. D is the partition coefficient. How does your element prefer to partition between the solid and the melt? So D is defined by the concentration of the element, in this case strontium, in the solid divided by the concentration of that element, strontium, in the liquid. So if you have the solid and liquid in equilibrium with each other, and you measure the concentration of a trace element like strontium in the solid and the liquid, then you can measure the partition coefficient. And when D is less than 1, so the concentration in the solid is greater than the concentration in the liquid, your element is said to be incompatible. The element is not compatible in the solid. And strontium, rubidium, samarium, neodymium are all incompatible elements. We'll be dealing with incompatible elements today. When D is greater than 1, or equal to actually as well. So the concentration of the solid is less than or equal to the concentration, the concentration in the solid is greater than or equal to the concentration of the liquid the element is compatible. Okay, so what happens in this equation as you take F to 0? Well, let's go the other direction. Let's say that F is 1. Let's go to the extreme. What happens to the concentration in the liquid relative to the concentration in the original solid when F is 1? Stays the same, because all of that trace element is now in the melt. So all the strontium that was here is now here. All right, so what about if F goes to 0? So you have an infinitesimally small degree of melt. It's 1 over d. So this ratio then, the enrichment of that trace element in the liquid, is controlled by 1 over the partition coefficient. So what kind of element would give you, as d goes to 0, as F goes to 0, what sorts of d values would give you the highest concentrations in the liquid? Small d. That's right. All right, so yeah.
I don't know if this is a silly question or not. Are there any other equations where you would model the same batch melting?
Oh yeah, this is the absolute simplest model. There are all sorts of melt models you could use. This is the absolute simplest. Yep. So this is just a starting point. For those of you that care, you can try fractional melting or aggregated fractional melting, or there's a whole bunch of melt models you can use. This is the starting point.
Do those melt models, are they very generalized? Would they only apply to particular areas and model that area really well?
What kind of area?
Well, where the melting would be occurring, or is it always the same?
Well, there's actually some debate about which melt model best describes what's really going on in the mantle. Yeah.
Is it the case that there would be just one? Is what I'm asking.
Probably not. Yeah.
I'm going to add that this, let's say, generalized simple equation works really, really well. However, when you want to actually go to more than one significant thing, you see that it doesn't work perfectly. And in fact, that's why, incremental melting or other forms of melting, where you can just imagine you've melted it by just a drop. And then that drop moves away from that matrix. And then you melt another drop, and it moves away from that matrix. So every time your D value is next to 0, and your F value is next to 0. I mean, your D value, your D value is next. So then you really concentrate the heck out of the highly incompatible elements. And sometimes it's observed that element abundances in mid-ocean ridge basalts, this element like barium, are more abundant than you'd ever predict.
So I'm going to show you guys some of the dirty laundry behind this equation, because a lot of my career is based on this and what I do day to day. What do we actually know and what don't we know here? We don't know F. We don't know the degree to which the mantle melts beneath the ridge or the hot spot. We measure that. That's the basalt, and we can reasonably guesstimate what that is if we assume what the MgO or something of the primary melt is. But yeah, I think we know this fairly well. We have no idea what this is unless the geophysicists provide us with some constraints. We have no idea what the mantle source concentration of a trace element is. Uh-huh. If you could give me this or this, yeah. D, how do we know D? Yeah, laboratory experiments. But it's not variable. It's highly variable. It's not constant. It's a function of a bunch of things. Pressure, temperature, composition, oxygen fugacity. Yeah. So this varies. Yeah.
So your initial concentration of your solid can also vary as a function of laterally? So you start melting and instead of melting from one place.
Well, the mantle is a heterogeneous place, so yeah.
So it's not even just even though the composition in one place, it's that you
You're just assuming like some average composition for the source. Yeah. Dirty laundry. This is really simple. Okay. So let's take this and plot this equation up. So on the x-axis we have F, so 100% melting here, no melting here, or rather infinitesimally small degrees of melt. Right? On the y-axis we have concentration of the liquid over concentration of the original unmelted solid mantle source. And then we have lines here that are contouring this figure for the partition coefficient. So, as F goes to 1, CL over C0 goes to 1. Right? Now let's look at what happens when we go to lower degrees of melt. If the partition coefficient is 1, the concentration of the liquid over the solid is the same. The element partitions equally between the solid and the liquid. So you have a horizontal line here. But if you have a really incompatible element, as D goes to 0, CL over C0 climbs as you go to really low degrees of melt. All right, so let's look at two different elements, rubidium and strontium, because they're important for this, that have two different partition coefficients. The D values for rubidium and strontium are different. Here I'm just kind of roughly guesstimating they're about a factor of 10 different. They're probably more than that. But this is for just the purpose of illustration. We know the rubidium is more incompatible than strontium. So what, just a second, what happens to the rubidium-strontium ratio as F goes to 0? Yeah, it gets big. Yep. Shouldn't go to infinity.
10.
It's going to go to the ratio of the reciprocals of the partition coefficients.
100 there on this one.
Yeah. Remember the limiting CL over C0 is 1 over D? So it's going to be 1 over D rubidium divided by 1 over D strontium. Yeah. So this is how, in the mantle, in the earth, when we melt the mantle, this is how we fractionate two trace elements from each other that have different partition coefficients. And this is really important because then we generate differences in what will be the parent and daughter ratios for isotope systems. Yeah.
This is probably a naive question, but you were just mentioning the errors in D and some of the problems with D. If you're using a system like rubidium, which is super duper sensitive, D is like getting asymptotic, it's blowing up.
Uh-huh.
So a small error in D could really change a lot what you would expect in the CL over C0.
Uh-huh, yeah, that's right.
So my question is, why don't you use systems that have like a D equals 2 or 4, which are much more well behaved at low melt fractions, that the error, like, you know what I mean? You can, even if you have the same kinds of errors on D, you have much better.
Would love to, but we don't have systems down, parent-daughter systems, where both of them are. I mean, that's the fundamental limitation, is we got to use the radiogenic isotope systems that God gave us.
So there's no
and we're limited. Well, we have one system where we have, for example, rhenium, which is pretty incompatible, but osmium is compatible. So you have a pair where you have one trace element that's compatible and then the daughter is compatible. When you're talking about rubidium, strontium, samarium, neodymium, lutetium, hafnium, you're dealing with two incompatible elements, parent and daughter. Uranium, lead, uranium is incompatible. Thorium is incompatible. Lead depends on a lot of things, whether or not it's compatible or incompatible. But yeah, I mean, all right. So here's a timeline. Rubidium-strontium ratio on the y-axis. In the beginning, God didn't give us two compatible elements. So we're going to deal that have a parent-daughter relationship. We're going to deal with rubidium and strontium here. We're going to say it's, 2.5 billion years ago. This piece of, we're going to call it primitive undifferentiated mantle, if such a thing ever existed, melted. And the melt, the rubidium-strontium ratio of the melt is going to depend on F. So as F goes down, the concentration in the liquid or the concentration of the solid goes up for rubidium, but not as quickly for strontium. So for small f, rubidium-strontium is very high in the melt, and for larger f, rubidium-strontium gets lower until you get to 100% melt, and rubidium-strontium better be the same as what you started with. Okay? Now, I haven't talked about how we calculate the residue, but it's just mass balance. The rubidium-strontium ratio of the residue is always going to be lower for rubidium-strontium than what you started with. And the more you extract melt from that residue, the lower the rubidium-strontium of that residue is going to be. Because you're extracting rubidium more efficiently than you're extracting strontium. Because rubidium is more incompatible than strontium. Right? No one's raising their hands. Not too many people are frowning. Okay, let's do samarium-neodymium. So forget about rubidium here. Samarium-neodymium, well, neodymium has a partition coefficient that's similar to strontium. Now, samarium, its partition coefficient is very close to samarium. Now, this is the trick with this system, this isotope system, is that you don't fractionate parent and daughter very much. Parent and daughter are both incompatible, but their incompatibilities are very similar. Their partition coefficients are very similar. Neodymium, though, is slightly more incompatible than samarium. So what happens when you melt the mantle? Remember how the rubidium-strontium ratio, the parent-daughter ratio, increases in the melt? When you melt the mantle, a primitive mantle reservoir. Well, what happens with samarium-neodymium? Because neodymium is slightly more incompatible, the samarium-neodymium ratio in the melt is lower than the samarium-neodymium ratio in the residue. And of course, the absolute ratio is a function of the degree of melting. So at 100% melt, the samarium-neodymium ratio should go back to what you started with. Yep?
Is neodymium always more incompatible than samarium? Depends on the temperature, pressure, composition.
During upper mantle melting, it should be.
So it's always the case.
Well, I don't know about lower mantle melts. That's a good question about lower mantle melts. I'm not sure. We have experiments for partitioning down to like 26 GPa, but then you have to extrapolate down to 120 to 130 GPa, and none of the experimentalists can tell me if calcium perovskite actually exists as a separate phase, and that's really going to tell you what happens with samarium-neodymium. I would love to know what the partition coefficients are for samarium-neodymium at the base of the mantle, because then you could predict what the isotopic ratios would be for any melts down there, but we don't know what the partition coefficients are. Yep.
I was going to say, how well do we know the partition coefficients, for instance, these two systems at high pressures and high temperatures?
Yeah, I mean,
What, you're saying some samarium and neodymium are very close?
yeah, okay, it depends on a lot of things, right? And like one thing that really matters is the lithology that you're melting. So if you're melting a portion of mantle that is brititite, then samarium-neodymium is going to be controlled primarily by CPX. And say you melt lithology that is dominated by, that's primarily a mafic lithology, then you're going to have a lot more garnet present, and then garnet's going to start flexing its muscles with samarium neodymium. So maybe even if we did know samarium and neodymium really well, the partitioning really well in the laboratory, we don't necessarily know what phases we're dealing with in the mantle source.
I guess I'm wondering, the question is how sensitive samarium and neodymium are similar, I mean, are the same amount approximately in compatibility? Could they flip in terms of, depending on the...
I don't think so. Not in the upper mantle, but the lower mantle is different. I mean, the reason we know they don't flip in the upper mantle and they haven't flipped over geologic time is because you have this beautiful isotope array in strontium neodymium isotope space. So that first figure I showed you from Al Hoffman's paper, if they flipped, sometimes you would see a lot of scatter.
I'll add to that by saying that, on average, if you look at rocks in the continental crust, the most continental crust or granites or even dirt out there, we actually tend to know their rare earth capture percentage. The amount of rare earth divided by chondrite. And what is extremely typical is fractionation of samarium and neodymium by 30 to 40%. We don't get factor of 2 variation in this ratio. We only get 30 to 40% in most lavas. And if you look at mid-ocean ridge, those that have just the slight depletion, the samarium neodymium fractionation in just the lava alone is over 10%. So the system is really not varying all over the place. And because they're both rare earths, meaning they're both 3+, and their ionic radius are very similar, you wouldn't even have a prediction that they're going to be grossly different.
By comparison, you can get a couple of orders of magnitude fractionation for rubidium strontium because their partition coefficients are so different. So just to compare everything, samarium neodymium, the melt has lower samarium neodymium than the residue. For rubidium strontium, the melt has higher rubidium strontium than the residue. Okay, so that's step one. How do you fractionate two trace elements that have parent-daughter relationships? Okay, so step two then is, after you fractionate the parent from the daughter, how do you generate isotopic differences? Well, the key is to wait and give 87 rubidium time to decay to 87 strontium, or give 147 samarium time to decay to 143 neodymium. Okay, so let's look at the rubidium strontium system. 87 rubidium decays 87 strontium. Half-life is about 50 billion years. So let's think of this in terms of decay constant. So what's the relationship between half-life and decay constant? Really easy, the natural log of 2 divided by the half-life in years. Okay, so let's look to see how rubidium-87 generates 87 strontium with time. So here's the simple equation. Here we have the strontium-87 that we would measure in the laboratory today. Here's the strontium-87 initially that your system started with way back in time, where time is t. Lambda is your decay constant. And 87 rubidium is the amount of 87 rubidium that you had in your system. Actually, that you have in your system now. Okay. Now, a fundamental aspect of isotope geochemistry is that we can measure isotope ratios much more precisely than we can measure concentrations. So we go through and divide every single term here by an isotope of the daughter, so an isotope of strontium that is both stable, so it doesn't change as a result of radioactive decay, and it's not radiogenic, so it's not itself increasing with time because it's a product of decay. And 86 strontium fits the bill, so we divide every term by 86 strontium. So we have now is an equation where we have 87, 86 strontium that we can measure in the laboratory. It's equal to the 87, 86 strontium ratio initially in your system plus 87 rubidium, 86 strontium ratio that we can measure times e to the decay constant t minus 1. Real quick, so the form of the equation here is just a line. Y equals the y-intercept plus x times the slope. Isochrones. Okay.
That 87 rubidium, that's initial concentration of, because that's changing too, right?
That's the initial that you started with, but that's going to change with time.
87 rubidium is what I'm.
That's changing, but it's very slight, right? Because over the let's say worst case scenario, t is 4.5 billion years,
Okay, so
right? Okay, yeah, it's pretty slight. There's actually we could add another term to keep track of the change in 87 rubidium, but we're not doing that here. We're not dealing with 6 decimal place precision. Yeah, very good point. In fact, let's illustrate that point. This isn't flat. This line is actually slightly negatively sloped. Well, actually, no, it's not, is it? Because that rubidium is decreasing while strontium is increasing. So yeah, that line is actually slightly negatively sloped. Very, very slightly. Because the time scale involved here is very small relative to the half-life of rubidium. Frankly, if I were to plot the true slope there, I bet none of you could see it. So, okay, so here's the question. When 87 rubidium, 86 strontium is high in this equation, what happens to the 87-86 strontium ratio over time? It's really easy. A seismologist has to answer this question. Because seismologists love equations, even ones that are so simple. Increase this, increase this. When 87-86 strontium is low, strontium 87-86 also increases, but at a slower rate. This doesn't decrease. All right? Okay, so let's take that y equals b plus xm equation, and let's show this in an isochron diagram, real simple isochron diagram. So the x-axis is 87 rubidium over 86 strontium, right there. So that's the parent-daughter ratio. And the y-axis is 87 strontium, 86 strontium. So at t equals 0 in this equation, at the very moment when you had a piece of mantle that you melted, thereby generating a residue, at t equals 0, the strontium isotope ratio for the melt, the residue, and the original source are all the same. But over time, as 87 rubidium atoms decay to 87 strontium atoms, the melt migrates up in this direction at a rate that's faster than the mantle residue migration up in this direction. Why does it not go directly up? Anybody? For the reason you pointed out. For every atom you lose here, you gain an atom there. All right? So how do you extract an age from this? Well, first, if you draw a line through these points, that line will intersect the y-axis. That gives you the y-intercept. That y-intercept, even at some time over 1 billion years or 2 billion years, that y-intercept tells you the initial 87, 86 strontium that you started with. So while we don't have a time machine, we do have the isochron so we can back out what that initial 8786 strontium was. So we can measure this, we can measure this, we know this, lambda, and so we can back out what the initial was, even after time t. And how do we get an age? Well, e to the lambda t minus 1 is the slope. So the slope, m, which you can measure on this plot, equals e to the lambda t minus 1. What do you not know? T. So t, just solve this equation. T equals the natural log of the slope plus 1 divided by the decay constant. And there's your age. Now, the key for this to work is that you need to have at least 2 points to define a line. Right? Because you have an equation here with 2 unknowns. You don't know the initial 8786 strontium, and you don't know T. So you need to measure this and this in 2 different rocks. Right? Okay, so how does this turn into strontium isotope evolution with time? How does fractionation of rubidium from strontium change strontium isotope ratio of the different reservoirs in the mantle with time? So, okay, 2.5 billion years or so ago, you melt the mantle, you generate a melt that has high rubidium strontium and a residue with low rubidium strontium. What then happens to the strontium isotope ratio? Well, the strontium isotope ratio is increasing over time in this reservoir. The rubidium-strontium ratio is constant, but rubidium is always decaying to strontium. Rubidium-87 is always decaying to strontium-87, so this reservoir is always increasing. And then melting occurs. You generate melts with high rubidium-strontium, so now the rate of increase of the 8786 increases. And the residue has a lower rubidium-strontium ratio, so the rate of increase is lower than the original mantle reservoir. Of course, this isn't just so simple. It also depends on the degree to which you fractionated rubidium from strontium. So if you really fractionated rubidium from strontium in the melt at low degrees of melt, then your 87-86 strontium ratio is going to climb much faster here. This, by the way, becomes your crust than it does in this case where maybe you extracted more melt from the mantle. Bill? Okay. All right. And of course, the more melt you extract, the more depleted your mantle residue is. And so the lower the 87-86 strontium that it ends up with over time. The same thing for samarium neodymium. So I'm not going to torture you with this. It's the same form, y equals b plus xm. You have the parent-daughter ratio, the initial 143, 144. E to the lambda t minus 1 is m. Here's what you measure in the laboratory as well. And in this case, the half-life is a little bit more than twice as long. Okay, so you can set up the same kind of isochrone diagram, but what's fundamentally different about this particular isochrone diagram compared to the rubidium-strontium system? Not Bill. That's right. So the samarium-neodymium ratio in the liquid is lower than the residue. But remember, for strontium isotopes, in the rubidium-strontium system, the parent-daughter ratio, rubidium-strontium, is higher in the liquid and lower in the residue. So it's flipped. Okay? And everything else applies. You can calculate an age from the slope, and you can back out what the initial neodymium isotope ratio was. Look at neodymium isotopes versus time. How does that change as a function of the samarium-neodymium ratio? Well, okay, so you have a samarium-neodymium ratio of your melt is lower than the mantle residue. So what happens? The neodymium isotope ratio of your melt doesn't increase as quickly as it does in the residue. Oh, by the way, the residue ends up being something that probably is melting beneath mid-ocean ridges today. And the melt ends up becoming something that's probably not unlike continental crust. So you guys want to make a prediction for what the neodymium isotope ratio for the melt is relative to the neodymium isotope ratio of the residue? Geophysicists? Morbs versus continental crust. It's too easy. A relative difference. Should morbs have higher or lower? 143, 144. Morbs are modern day melts of a depleted reservoir. That's right. So remember, the neodymium isotope ratio doesn't change between the residue and the melt on day one. So the neodymium isotope ratio that you measure in that morb should be identical to the neodymium isotope ratio in the residue, which is fortunate because we're probably never going to drill a hole that deep, at least not in my lifetime. That's right. So that's a good point. So if you melted the mantle residue in the past, say you look at 180 million year old oceanic crust, those morbs would be plotting up here, right? Because they've been given time to have 143 ingrow as 147 samarium decays, and they had a. I'm sorry. Yeah, you're absolutely right. Yeah. So morbs erupted 180 million years ago would be over here. Yeah, that's right. Thanks. All right. So the complexity of strontium and neodymium isotopes. Everybody wants a solution. When did the mantle melt to make these different reservoirs? Well, okay, so there are a bunch of problems here. The strontium isotope ratio that you measure in a lava today, well, that lava is a melt of a reservoir that may have had a really complicated history. But the first thing you got to ask yourself is, that mantle reservoir, when did that mantle reservoir form? And what degree of fractionation generated that mantle reservoir? And these are two things, these are all is a hugely unconstrained problem. So, for example, melts generated at 4 billion years ago at F equals 3% may end up having the same strontium isotope ratio as melts generated by 1% melt at 2.5 billion years ago. Okay? So the degree of melting and the time of the melting event are a couple of unconstrained problems. We could measure the strontium and neodymium ratios in basalts, but then we have to make some educated guesses about the history of the mantle sources that generated those basalts. Okay, so how do we then go from here to here? Well, let's follow an example of melting happening at 2.5 billion years ago or so, where you have a mantle residue that's generated that generates high 143, 144, and a melt that generates lower 143, 144. And you have a mantle differentiation event at 2.5 billion years ago for strontium isotopes where the melt ends up with high 87, 86 and a mantle residue that has low 87, 86. How can we take what we know here and translate it over here? Okay, so this field is defined by isotopic measurements made on morbs, where morbs are thought to sample a depleted mantle reservoir. So morbs, which have high 143, 144, and low 87, 86 strontium, should reflect the isotopic evolution of a depleted reservoir, a residue that once had melt extracted from it. So here you go, high 143, 144, low 87, 86 strontium. Here you have the residue will have high 143, 144, and the residue will have low 87, 86 strontium. On the other hand, continental crust plots way down over here off the figure. Continental crust is the melt, ancient melt extracted from the mantle. The melt should have high 87, 86 strontium and low 143, 144. Sure enough, you have low 143, 144 and high 87, 86 strontium. And the longer, the deeper in time you go to generate continental crust, the more potential you have to have incredibly radiogenic strontium and low 143, 144. All right, so let's look at this really simple Excel spreadsheet. And let's think about how we can use this spreadsheet. So the first thing that we do in the spreadsheet is we assume a uniform silicate Earth that underwent melting at some point in time. And you're going to decide when the melting event happened. Pick 1 billion, 2 billion, 3, back to 4.5 billion years ago, you can decide to have the mantle undergo a melting event. And then you can also decide to what degree that mantle reservoir melts. Did you extract 1% mantle or 5% mantle or more? So start with this, an initially uniform silicate Earth. You're going to extract melt at different times and different degrees, and look to see how the strontium and neodymium isotope evolution varies for the melt and the depleted residue, the portion of mantle from which melt was extracted. And then we're going to open Pandora's box and play around with our assumption for the initial composition of the silicate Earth. Okay, so let's I don't know if any of you have had better luck with internet here than me. Bill has it. Yeah. So the first thing we're going to do is just look at this really quick. Oh, Jessica, what?
I was just going to ask if your age is your time ago from now or age from...
Time ago from now, yep. Good question. Is it time after formation or time ago from now? It's time ago from now. How many billion years ago? So strontium versus neodymium isotopes. The gray symbols are an ocean island basalt data set. The black symbols are a mid-ocean ridge basalt data set, and there are some pretty bizarre morbs here. Most morb concentrates right here where the yellow symbol is right now. Ocean island basalts in general tend to extend to higher 87, 86 strontium ratios and lower 143, 144 ratios on average. I've plotted bulk Earth here. That's not going to change until you guys decide to make it change, and then Bill will be really angry with you. So we're starting with what Bill wants the bulk Earth to be. Continental crust and depleted mantle, these 2 points are going to move around as you play around with the values in this simple toy model.
Can I just stop for a second?
Yeah.
If you're interested, it's not whether or not you believe the Earth looks like X, Y, or Z, but it's very, very typical, common starting point that people will say, let's assume the Earth is a C1 chondrite. It has the best match to the sun. Well, you can go in and do that by just increasing the rubidium content by a factor of 8. And see where the bulk Earth strontium content, isotope content goes. Yeah. C1 chondrite has a factor of 8 more rubidium than the Earth. If you want, just make the factor of 10.
These are
Change the ratio or the?
Oh, yes. So you change the values here in the yellow boxes. Let's just go through this really quick. Age in billions of years, so 2 would be 2 billion years ago. 0 is fractionation happened today. I would not recommend making that number bigger than about 4.5556 billion years old. You can change the partition coefficients for rubidium, strontium, samarium, neodymium. Yeah.
Can we change the whole fraction equation?
If you want, yeah. Have fun.
Sure. You own it now.
Yeah.
Well, I mean, if you change that, is it still internally consistent?
Well, I don't even know if this is internally consistent. We're going to find out.
But I mean, are there other parameters that if you assumed the different melt fraction equation that you would have calculated them differently?
No. No. The only thing that matters is fractionating rubidium from strontium and samarium from neodymium. And how you decide to do that, it's up to you.
Let me just add, you worry about internally consistent, right? And perhaps you're just challenged by the fact that you need to have conservation of mantle and other things, right? Don't know. Composition of the Earth, that's one of the things I'm debating with.
Did you just say that?
Yeah.
Is that on tape?
Yeah.
Here, Bill, I want you to speak into this.
We know to 6 significant figures.
I was like, this is going to be my redeeming moment. Bill, sign here.
So we don't know the abundance, the rubidium-strontium ratio, the samarium-neodymium ratio of the depleted mantle, and we don't know it of the continental crust. But of all the things, we sometimes, depending on the day of the week, think we might know the bulk Earth, and sometimes we think we know the composition of the continental crust. But that's about as strong as we get. So don't worry about whether the system is self-consistent. There's too many knobs. Josh has a question.
Hey, so I'm thinking back to something that Bill said earlier, which was that the ratio of the decay is like 2 to 1, or neodymium has a half-life that's twice as big as samarium.
Uh-huh.
So,
Samarium's half-life
yeah.
is twice as big as rubidium.
Oh, it's twice as long.
Neodymium's not decaying.
Okay.
So there are a couple things going on here.
48 million years and 103 million years.
106.
106.
So, yeah, that's fine. 1500 is good enough for me. So I want you to look at the relative differences in the range on this axis compared to the range on this axis. Now keep in mind that the half-life is twice as long, controlling this axis, so you don't generate isotopic differences as quickly, and the parent-daughter fractionation is much smaller, a couple of orders of magnitude smaller. So here, the decay is more rapid, and the parent-daughter fractionation is much greater. So how would that feed back into the total difference that you see on each axis? What decimal place are you seeing variability here? What decimal place are you seeing variability here? Right.
I'd like to add just one more historical sociological phenomenon. I'm a second-generation neodymium isotope person. I did my PhD with Malcolm McCulloch, who was a co-student of Simon Jacobson and Don McCulloch in the Wasserberg lab at Caltech, who was one of the first pioneering labs to actually technologically achieve the measurement of this isotope. So I got my PhD in the early 80s, I was doing it down at Australian National University. So this, I mean, some of you probably have had classes on Apollo. He was a first generation neodymium isotope person. So this is a relatively new system. It really is.
40 years.
That's still new.
38 years, I guess. So you'll notice here, so these are the bulk silicate earth. This is the initial starting composition that we're assuming in the model. Or this is, sorry, the present day bulk silicate earth composition. You'll see that that matches what we have here. And this is the standard model for the composition of the earth. So the rubidium-strontium ratio, the strontium isotope ratio, the samarium-neodymium ratio, and the 143-144 neodymium ratio. If you want, you can try to play around with something like this, which is a composition for the bulk earth that has been suggested in the last decade or so. This is the Boy and Carlson kind of stuff, if you're familiar with it. Okay, so let's see what happens when you change the timing of differentiation. So let's say that differentiation happened 4 billion years ago instead of 2 billion years ago. Isotopic differences become more dramatic. The melt extraction was the same in this case, but you've simply given the depleted mantle reservoir more time to ingrow 143, 144. Yeah?
So Bill said we know what continental crust is. Where is it on here?
It's the red squares.
Well, yeah, that's the model. I thought you said we knew it.
In terms of isotope space, I would assume, let me see if I would call it 7-1.
First, I don't know the age of average continental crust.
Yeah, so 0.71 is what I would consider to be.
Okay, so we've got the x-axis.
I wouldn't commit myself to a value, but
That's
I'll
the,
give you two significant figures. You should be able to, I guarantee you it's not 0.72 and it's not 0.0705.
so Sujay, remind me what value you used in Shishun's. You didn't calculate a strontium, did you? Okay.
So the best way to look at continental crust is to measure sediments, river sediments.
That's 7-1.
Well, that gives you the upper continental crust. And who knows what the middle and lower are.
No rubidium. It just drops off pretty quickly. So strontium is almost equally distributed in the upper and lower portions of the continental crust.
So we know the trace element composition of continental crust reasonably well. We know it better in the shallow region of the crust where we have access to the rocks, and we don't know it as well as we go deeper. We also don't know the average age of the crust, so it's hard to then figure out what the average isotopic composition of the crust would be. But okay, I mean,
the reason why I'm asking is because you can play around the things. You can move that yellow dot all over the place,
Uh-huh.
which is nice, and then you can say that, okay, I've got the yellow dot in the middle of the morb. But there's a lot more motion of that red dot, right? And so if we had something to anchor that on, that's more
that'd be really nice. The goal, of course, is to put that yellow dot on top of the morb field, right? Because the morb field is a melt of the depleted mantle. Modern depleted mantle. That's right.
Can I ask a question?
Oh, no, you can't ask me a question.
Can I ask them a question?
Yes.
No.
Is the system completely described by the red, yellow, and blue dots?
I'm going to quickly say no.
They don't have to.
Well, what else is there between the ball?
But Josh has asked a very good additional question. What else is there? So I'll ask my question. Is the system completely described by these three dots?
No, where's the core?
Okay, where's the core is a good question.
Has no rubidium, strontium, samarium, neodymium. So.
Down there, that's
Oh.
Right under us.
No, none of these elements should be in the core. I mean, they'll be in at a kilogram.
Oh, okay.
Out of 10 to the 18 kilograms.
How about the
10 times 20 1. What was the question?
How about the L as hidden reservoir?
Okay, so that's actually an extremely important answer. If you say that LLSVPs or anything else should also be considered, then we do not describe the system by these three dots, the bulk earth, the depleted mantle, and the continental crust. And in fact, I've heard somebody refer to it as the upper mantle. Right? Okay, so we actually do not know the volume of yellow dot.
It's about 90% of the Earth.
Say that again? 98% of the Earth? All right, then let me ask a question. What is the mass fraction of the continental crust? Mass fraction.
0.5% of the...
0.5% of the silicate Earth. That's a really good number you put in the pocket. All right, so how much of the budget of strontium on neodymium is in the continental crust?
More than that.
Yeah, about 15%. Some number like that.
Enrichment.
1.5. And in fact, just to put it in perspective, it depends upon whose Earth model you like. Because it goes back to that 10, 20, or 30 parts per billion uranium. If I'm going to speak from a 20 parts per billion uranium, then 15% of the budget of strontium and 15% of the budget of neodymium in the continental crust. And in fact, 40% of the heat-producing elements in the Earth are in the continental crust. So 40% of those heat-producing elements is in 0.5% of the mass. The system's extremely efficient.
Is that it, Bill?
Here to trust your numbers or something.
No, he doesn't. In fact, he likes delusional erosion.
So,
And that would translate immediately to say that 80% of the heat-producing elements are in the continental crust. Now I've made him work. You can see what he's standing.
No, I mean, I don't think we know. That's the problem. I mean,
I agree we don't know.
and I might be wrong. I'm probably wrong, but it's interesting to consider. I mean, all these models until a decade ago, models always assumed that this was fixed and this was pulled out of here and the residue was whatever was left over. But then, this is really exciting, is what can we do if we relax that constraint and let that point move around? And the Boye and Carlson paper argues that point moves up to here. It's pretty close to Morb. The Morb is actually pretty close isotopically to bulk silicate Earth if Boye and Carlson's interpretation is correct. So, okay. So you can do all sorts of things by changing the time that the fractionation event occurred. Of course, the fractionation event, melt extraction of the mantle, has been ongoing through geologic time. So what you're actually looking at here in this array is the sum total, all the integrated melt extraction events over geologic time.
so if we see that looks nice at 2 billion years, are we saying?
There might be some average, yeah.
1 to 3, or what are we?
Well, average continental crust. I hate to commit to a number, but people will say numbers like a couple billion years.
Between 0 and 4.5.
Yeah.
Yeah. What do you think, Bill? Do you like 2? 1.8? 2.5? 2.5 is a little old, probably. Okay, but then you can also play the game of the amount of melt that you extract. So extract 1% melt, or extract 10% melt.
I have a naive.
Yeah.
I'm sorry I'm beating this to death, but I'm trying to get this in my head, and somebody's still not clicking for me.
Okay.
So if the ratio of the decay, here's my direct question.
Uh-huh.
Shouldn't the best answer, the real answer, lay on a line with slope of -1/2, because that's the ratio of the decay times?
Oh, that would be true, maybe, but only if samarium, neodymium, rubidium, and strontium fractionated the same way.
Okay. Because that's what I'm like,
But
I'm trying to make
okay, put it this way. The ratio of the half-lives is 2 to 1, but the ratio of fractionation is something like
15% to
maybe factor of 2, I would say a couple orders of magnitude.
Okay.
Wow,
I
okay.
haven't thought about it. But yeah, it may.
Yeah, I'm thinking like rubidium, strontium, and continental crust compared to rubidium, strontium, and DMM
Yeah.
is probably more than 100. So what dominates this is the degree to which rubidium and strontium fractionate compared to the degree to which samarium and neodymium fractionate.
Yes, close to 100.
Cool, huh?
So, okay, so now I'm trying to understand, like, when can you say we did it? You know what I mean? Like,
Nobel Prize for this guy if he tells
you know,
me right
like,
now.
I'm not trying to be like, I'm not trying
No,
to
I know, and I'm
trying
sorry.
to, like, you can make the yellow dot overlap, but it seems like, you know,
There's not a unique solution for making that yellow dot overlap.
So
Yep.
Like, how can you do better?
I have sat down with beer friends talking about this problem many times. And many people have had this conversation. How do we really get at that?
Yeah.
I want to know where the red dot is.
I mean, I think
You can show
the
them the
first
red dot.
order problem.
That's my first question.
So the first order problem is, okay, let's say it's 2 billion years ago and 3% melt extraction.
And that's 3% of the whole mantle.
Well, of the whole mantle, that's right. So, but what if we change the composition of the mantle? So it's just, right? So the solution actually depends on what mantle composition we pick. I feel like a first order issue for us right now is to figure out what is the composition of the Earth. And then when we move beyond that, we can go back to the older question that we weren't able to solve.
Give me that red dot.
All right, so now Volk Earth just moved from here to here, and so did DMM.
But how can the whole Earth, the bulk Earth, have a composition of Morb?
It's not Morb. It's slightly less depleted than Morb. So
It's within the black, an ocean of black, though.
yeah, so there is not a nice little histogram here showing. But it's also, how do you define the bulk composition of Morb?
The average of all the blacks.
Yeah, do you weight it? How do you weight it? Do you weight it by concentration? Do you weight it by ridge segment? How do you weight it? I mean, there's enormous debate right now about how you come up with an average composition for Morb. We'd love to have that, because then you have an average composition for Morb. Does that really reflect the average composition of the depleted mantle? Can any of you suggest to me a way in which the average isotopic composition of the depleted mantle might not reflect the average isotopic composition of Morb, even if we knew the average isotopic composition of Morb?
Plumes.
Oh, plumes, that's one, right? So why would plumes change Morb but not tell us what the upper mantle is made out of?
You've got plumes getting sucked into the system.
What if you melt it twice?
Melt what twice?
Melt the upper mantle twice. You do 2 extractions of melt.
Mm-hmm.
This is assuming only 1 extraction of melt, right?
That's right. So in fact, it's probably many extraction events.
Yeah.
So this is just a simple 2-stage model.
And we should be modeling the OIE by changing the composition to jack up the rubidium to...
So what are OIB? What did, so Bill White, just a second. So Bill White sort of, one of the godfathers behind describing what we think OIB lavas sample. What are OIBs sampling? What did he tell us?
They're small-scale heterogeneity related to small-scale heterogeneity.
And where do those heterogeneities come from? Well, so that's the standard model that Hoffman and White and Hoffman came up with 32 years ago. Yeah. Subduction of oceanic crust and continental crust over geologic time. And so these arrays are pulling off towards perhaps different kinds of crust that were subducted and then remelted. That's right.
Do you need somebody to walk into the gaping hole and say maybe they're from LSVPs that have been there the whole time?
In order to answer that question, we need better trace element partitioning constraints. So this is the thing. We know what we're getting a pretty good handle on how trace elements partition during upper mantle melting. And so when you look at trace element patterns, you guys have seen some of these spider diagrams. From these patterns, you can actually tease out signatures associated with continental crust, for example. But it's been really hard to figure out what other signatures mean. Well, if there are melts in the lower mantle, you're going to expect to see some really bizarre trace element partitioning going on. What we know about calcium perovskite, it does really strange things to trace element patterns that you.
Calcium perovskite.
Yeah.
That's
You,
interesting because it's not that easy to.
of course it's not, and that's why we don't have the data. And it's.
Calcium perovskite specifically.
Yeah. But calcium perovskite is going to be controlling the elements of interest here in a big way. And if we had better partitioning constraints, then we could start to look for the signatures that would be associated with calcium perovskite. A couple of signatures, for example, are, here's one. Calcium perovskite, barium, and strontium are incredibly compatible in calcium perovskite. Niobium, tantalum, titanium are not. Hafnium, zirconium are not. So you would expect to see really bizarre fractionations between the traditional incompatible elements and these high field strength elements, niobium, tantalum, titanium, hafnium, zirconium. In fact, we see hints of these kinds of fractionations in some ocean island basalts. But it's really hard to model these patterns in ocean island basalts using melts in equilibrium with perovskites, because we don't have great constraints on the partitioning.
So you're talking about really deep melts?
That's right. Well, did you ask me?
I said, do you want somebody to ask a stupid question, and then did.
That was a great question.
Actually, what she had said was the LLSVP, and it struck me as unusual that somebody translated that word into a zone where melting is.
If we have melting going on in the lower mantle, where you have a melt and a residue, the fractionations are going to be really, really different from what we see during melting in the upper mantle, with some telltale signatures. And if we had the right partitioning data, that we could start to look for these signatures.
I have a quick question. Are there any specific references that any review papers on this?
Yeah, Hirose, Corgny, I'm not sure if I'm pronouncing it right. These are Cornier. This is 2005 papers. They went to the top of the lower mantle in terms of pressure, and 26 GPa. But then you got to extrapolate another 100 GPa.
If OIVs are containing recycled crust, why do they point off not in the right direction?
Excellent question.
You can't hear.
I was saying if OIVs are containing recycled crust as one particular model, why are they not pointing towards continental crust or towards? Yeah, sure. We've already established that the red dot is the red dot. But the trend as you go away from bulk silicate Earth, you're incorporating stuff that's heading off towards high strontium.
You got a couple of different trends here.
Well, yeah. So you've got
So there's one trend that goes out here, and this is what Bill White called EM2. You have another trend that goes down here. Goga, what do you call that one? That's right. And there's a big debate about what's pulling you this way, what's pulling you this way, and it's like, well, what kind of crust? Continental crust or pelagic sediments, or we don't really know. Okay. But pelagic sediments ultimately derive from continental crust weathering. Right? Silts and clays that are settling out in the ocean from rivers. So this is all, and that would mean that this is all just kind of different flavors of continental crust. But
Pretty different places.
what about oceanic crust? What does oceanic crust end up looking like? I mean, if you take modern day subduction rates, extrapolate back in time, so you got 20 cubic kilometers of oceanic crust going into the mantle over 3 billion years. How many cubic kilometers of oceanic crust do you have in the mantle, assuming the mantle is not a cannibal and it stays down there? 60 billion cubic kilometers. Does anybody know what mass fraction of the mantle that is? It's a little high, but I'll go with Bill.
7% is the actual number.
And I think that's a lower limit because, again, we're using modern subduction rates. So there's a significant reservoir of oceanic crust that we've stuffed into the mantle over geologic time. So it'd be awful nice to know what that would look like. And then we go looking for the isotopic signatures associated with that. All right, but that's hard to do. Yeah?
Space is back there just.
Oh, sorry. Sorry.
I don't know if this is a silly question. So we know all of these were formed by just different processes. Or can you just use different the melt fraction equations instead of trying to treat them all the same, just all the time? Why don't you treat them differently? Since we know they're different, and change your melt equation for whatever process. Maybe it's different for the subduction or when it's rising. Maybe it fractionates differently.
Oh, yeah, absolutely. So
I mean, we keep throwing them all on the same.
So let's say we take this piece of modern morb and at a subduction zone today. Parent-daughter ratio is fractionate, and that piece of morb that's undergoing dehydration reactions to become eclogite. What happens to that morb? What happens to the rubidium, strontium, samarium, neodymium, uranium, lead, lutetium, hafnium ratios? All these things that we can then track with isotopes. What happens to these trace element ratios? A lot of people are working really hard on it, and I don't believe anything. Yeah, this is, it's hard to, this is why people call this the subduction zone factory, and it's a black box, because stuff is going into it, and we know stuff comes out of the arc, but what remains in the slab to go down into the earth to become this reservoir that we hope to tap with ocean island basalts? We don't know the composition of this. Okay, what's Bill White's answer? Bill White thinks it plots right here. Stuff that was subducted 2 or 3 billion years ago, oceanic crust, subducted 2 or 3 billion years ago, ends up over here. I'm not sure I know if that's true, yeah. Okay, so there are a bunch of problems here, right? Ancient subduction zones, they would have likely been hotter. So maybe it wasn't just simple dehydration of the slab. Maybe you also had slab melting. Okay, in which case you're going to have different fractionations of parent-daughter ratios altogether. Okay, what was going into the subduction zone 2 billion years ago? What did morb look like back then? Going back a few billion years, there are people that say that morb looked more like a komatiite. The Earth was hotter, higher degrees of melting. So we don't know what the protolith was. We don't know exactly what happened to it when it went down into the mantle. Probably different than what's going on today. So it's not clear that what's going on in modern subduction zones is a good analog for what went on in Archean subduction zones. Pardon?
We have some ophiolites.
Yeah, that's stuff that didn't get subducted, though.
These give information on the nature of the water.
Right, okay, so you have Archean greenstone belts. Are those mid-ocean ridge basalts that have been hanging around in the cratons for a few billion years? I don't know. Yeah, these are really important questions, and we don't have the answers right now. I'm hoping one of you guys will have the answers for me.
How many of these things we're interested in are fluid mobile as well?
Well, samarium and neodymium aren't terribly fluid mobile. Rubidium is incredibly fluid mobile, and strontium is moderately so. Yeah. But that's just if the slab is being modified by dehydration. What if you're actually melting it? What if the thermal regime of the subduction zone allows you to melt a slab? Then you have to worry about not only dehydration and fluid mobility, but fractionation of the trace elements by melt extraction from the slab. Yeah.
We sample bonanites,
Huh.
so we do have some of these weird melts which may or may not be melted slab.
Yeah, what are bonanites?
Huh?
Yeah, what are bonanites? Or adachites? People think that these might be modern melts of the slab. Might happen in subduction zones, but other people would shoot me right now on the spot for having suggested that. There's so much agreement. Yeah.
Is there any other system that you can project on a third axis as that cool busy
And what, I mean, you could. I mean, hafnium isotope, well, choose your favorite isotope system.
I mean, something that you have better constraints on that maybe would be less dependent on potential melting issues.
Bill?
Actually, I was thinking that you would even review for them, ever so briefly, some portion of Jackson and Jelinek. Because what he was saying was actually that, what is it, your figure 1 or figure 4, that where you show the difference between the parent-daughter ratio of lutetium active, samarium, neodymium, rubidium, strontium, radioactive.
For different compositions of the Earth, or?
Just the systematics of that distribution of isotope. Can you pull up that figure? It's your figure.
Let's see here.
I think it would put in perspective for Nate at least, and also others that.
I'm not sure what you're after here, Bill, but I'll just, right here?
Up above.
That's pretty. I like the little loop-de-loops.
You like that? To the top?
Yeah.
You want this?
Right. Just explain what figure 8 is doing. You're not going to do it.
Sorry.
They're epicycles.
Okay. All right, so what do we have going on here? So this is a spider diagram for the uninitiated. So what do we have plotted here? We just organize the elements in order of decreasing incompatibility. Well, I think it's useful for people to hear it again, maybe. I don't know. Or you can boo me and tell me to go away, and I will. So rubidium is really incompatible. Lutetium is incompatible, but not as incompatible. And then on the y-axis, we normalize the concentration in our sample, which is the red line. We divide that concentration by the concentration in some primitive mantle composition that Bill came up with. Okay? And so what you end up with is generally a smoothish line that tells you something about whether or not your sample is depleted in incompatible elements relative to McDonough and Sons bulk Earth. By the way, where does McDonough and Sons bulk Earth plot here? A horizontal line anchored at 1. That's right. And if a sample plotted up here and a slope down, it would be enriched in incompatible elements. Okay, so going to the top here, I have plotted 6 elements. 3 parent-daughter pairs. Sure.
That question.
Yeah.
Where is he at?
Here.
Yeah.
Let's move that annoying sticky note. So, actually, Bill, do you want to explain this? I'm not sure why I'm explaining this right now.
Bill might show the isotope plane, a three-dimensional projection.
Yeah.
And Nate was asking, are there other isotope systems that would help us to understand it?
Yeah.
So the rubidium-strontium system is shown in one loop here, the samarium-neodymium system is shown in another, and the lutetium-hafnium system is shown in another. And in fact, you could add the uranium-lead system.
And that's shown further down. Yeah, we use that. So rubidium decays with strontium. X-axis is just the incompatible elements organized from left to right, decreasing compatibility. Yeah. Now, so rubidium, strontium here, samarium, neodymium. You'll see there that the fractionation for samarium, neodymium isn't as large as for rubidium, strontium. And then lutetium, hafnium. That's a system we didn't discuss, but it's very similar to the samarium, neodymium system, in that the daughter, hafnium, is more incompatible than the parent, whereas with rubidium, strontium, the daughter is less incompatible. Okay, so here's a quick question for you then. What would you expect the slope of a hafnium isotope versus neodymium isotope plot to look like? Global ocean island basalts and morbs plotted. Remember, the strontium neodymium plot is negatively sloping through the data array.
It's the same way around as positive.
That's right. That's right. Positively sloping line. So you introduce another isotope system, you're going to deal with the same problems. You don't know the degree to which lutetium, hafnium were fractionated in the slab, either by melting or by fluid mobility. Fortunately, lutetium and hafnium aren't too mobile and are not very fluid mobile. It's like samarium, neodymium. But you still don't have great constraints on how the ratio of these two elements changed in the ancient slab. Yeah. I'm not trying to discourage you, but a lot of people have the feeling that when they introduce another isotope system, they'll have the answer, but it's usually more questions. You better constrain the problem.
So what do you do now?
What do I do now?
Yeah.
Well, if I tell you,
If you
then
introduce another one, it makes it more difficult, but where you're at now, you're sort of stuck, right?
yeah. Well, that's it's a problem, and there are actually some ways to go forward right now. An important way to go forward is in the laboratory.
I mean, would having
For
other
example,
samples maybe relax something
well,
as well?
no, you can talk to a non-mnemonic, and you should, for example, and talk about how these trace element ratios are fractionated by melting mafic protoliths, so eclogites and peroxenites, and what kinds of fractionations you expect. How does rubidium, strontium fractionate? How does samarium, neodymium, lutetium, hafnium fractionate when you melt things that have mafic protoliths? Now you trying to get rid of me, or are you trying to? Oh, okay. We can talk more about this. I think really quickly though, I think osmium isotopes give us a nice clue About the possibility of mafic protoliths cycling into hotspots. And we can talk about that if you want, but I think everybody would rather go eat cookies and drink tea.